Okay, so for this one, we have to solve for Vt for the following circuit. So let's draw the circuit when t was less than 0. So when t was less than 0, this switch was opened. So our circuit will look like the following. Okay, so pretty much we're going to assume that the circuit looked like this for a long time. So this region short circuits, and this region becomes an open wire. So this is 30 ohms, this is 40 volts, this is 50 ohms, and this is the voltage, and we have a current passing through here. Okay, so let's first find the current. So it's going to be so if we do a mesh like this, it's minus 40 plus 30 I1, let's call this I1, plus 50 I1. Okay, and I1 gives you 1 over 2, and since I1 is moving in the opposite direction of I, so then that means I is minus 1 over 2. Okay, and this is going to be your I of 0 when you flip this switch on, because the current passing through inductor can change instantaneously. Now the second part, we need to find the voltage at the capacitor. So what the voltage here is the same as the voltage here. So let's just find the voltage at this resistor, which will be the same as the voltage of the capacitor here. So V will be equal to 50 times 1 over 2, and that's 25. And that's going to be V0, because same thing, when we turn the switch on, the voltage here, which is going to be the voltage at the capacitor, can change instantaneously. Now let's draw the circuit when t is greater than 0, greater than or equal to 0. This switch is flipped. Hold on, there we go. So our circuit pretty much looks like the following. Okay, so the thing we see here is that we have this closed wire with no resistance or anything. That means any of our current in this portion of the wire won't ever reach here, because they're all just going to go through here instead, as current will choose a path that has no resistors instead of going through a path that has resistors. That means this portion of the circuit we can just fully ignore. So we just have a circuit that looks like this. This is 0.4 henries, 50 ohms, and this is 20 microfarads, and that is 2 times 10 to the minus 5 farads. Okay, and then we have the voltage here. This is what we're trying to find, and the voltage here is going to be the same thing as the voltage here. So I'm going to label this region to be V. Now I'm going to set some directions of current. I'm going to have I1 here, I2 here, and I3 here. Okay, so for I2, to represent the voltage there, it's going to represent the current passing through this resistor, it's going to be V over 50. To represent the current passing through here, it's going to be the capacitance times the change in voltage over the change in time. And to represent the current passing through here, through the inductor, it's going to be 1 over L times the integral of V dt plus I at 0 t, the initial current passing through the inductor. Okay, now I want to get rid of this integral, so I'm going to differentiate this whole thing. So it'll be dv over dt time, so 1 over 50 dv over dt plus c d2v over dt squared plus 1 over L v times v. And then this is a constant, so this just goes away. Okay, so I'm gonna rearrange everything and have this just be alone. So it'll be d squared over d squared v over dt squared plus 1 over 50 times c. I'm dividing everything by c. Okay, plus v over LC. Okay, wait, sorry, made a small mistake. This is supposed to be dv over dt plus 1 over LC, and then v here. Okay, there you go. That's more like it. I'm going to have s to be dv over dt, so it'll be s squared plus 1 over 50c s plus 1 over LC. Okay, so now I can use the quadratic formula to solve for s. So it'll be minus 1 over 50c plus minus the square root of 1 over 50c squared minus 4a times c, LC, all over 2a. I can break this up, and this region I can just call it 2 times 50 times c. This I can have the square root of 4, which is still 2, and I can represent all of this with just 1 whole square root. Now I can break this up into 2 slots. This and this cancels out. This I can represent this as the square root of 4 squared. Okay, this is still 4, and then I can put this into here, which turns into 1 over 2 times 50 times c squared. Okay, so this is gone. Now I'm going to square root all of this and then square it, and that's pretty much just this. And then we get the following. This is alpha, this is alpha, this is omega. Alpha being your damping factor and omega being your undamped natural frequency. So we can just draw this. And this is equal to S1 and S2, them being your natural frequency. So alpha is pretty much equal to 1 over 2 times the resistance times the capacitance, and omega is equal to 1 over the square root of LC. So we're going to check the following. If alpha is greater than omega, then we have an overdamping case, and to find the voltage passing through the capacitor, it's going to be equal to A1 ES1T plus A2 ES2T. Now if they're both equal to each other, then we have a critically damped case. So the voltage passing through the capacitor will be A1 plus A2T e to the power of minus alpha t. Now if omega is greater than alpha, then we have a underdamped case. And in that case, Vt is equal to e to the power of minus alpha t times A1 cos WDT. WD is supposed to be your damping factor, so it's not this. It's pretty much, so if this is greater than this, then you're going to have an imaginary number, and whatever is being times by that imaginary number is WD plus A2 sine WDT. Okay, so we're going to find alpha, which is 1 over 2 times the resistance, which is 50, times the capacitance, which was 2 times 10 to the power of minus 5, and that should give you 500, and that's in radians per second. And now omega, that's 1 over the square root of the inductance, which is 0.4, times capacitance, which is 2 times 10 to the minus 5, and that's equal to 353.55 radians per second. Okay, so now start putting stuff in. Wait, sorry. Now we see that alpha is greater than omega, so that means we're going to be using this formula. So we have to find S1 and S2. So S1, S2, that gives, so we have minus 500 plus minus the square root of 500 squared minus 353.55 squared. So your S1 and S2, if you were to solve for them, you should get minus 146.44 and then minus 853.365. So now plugging everything in, so we have Vt equals A1E minus 146.44T plus A2E minus 853.365. Now, the next part is to solve for A1 and A2. So this is the tricky part. So we know that when T was 0, V was 25. So we can just do this, replace this with 25. A1, e to the power of 0, which is just 1, plus A2. Okay? Now we have to, we need another formula. So we can, find, because we have right now have two unknowns and just one equation. So what we're going to do is differentiate all of this. So it'll be d vt over dt equals a1 times minus 146.44 e minus 146.44t plus a2 times 850 minus 853.365 times e to the power of minus 853.365. Okay, so now we have to solve for dvt over dt. So what we should do is do the following. So we're going to use this formula, and I'm going to view it when t was equal to 0. Okay, so when t is equal to 0, the voltage was 25, and the current passing through the inductor was minus 1 over 2. Okay, so what we're going to do is put 25 over 50 plus c dv over dt plus minus 1.1 over 2. And you see this and this will cancel. So if c dv over dt for 0 is equal to 0, so this is also gone. So that means dv at 0, dt is equal to 0. So I'll put this here. So this is gone, this is gone. Alright, good. Okay, there you go. So now we have two equations and two unknowns. Now we can solve for a1 and a2. And you should get the following. A1 should be equal to 30.16 and A2 should be equal to minus 5.156. So now we can write our final answer. So Vt is equal to 30.16 e to the power of 146.44 t plus minus 5.156 e to the power of 853.365, and this is in volts. Okay, and this is your formula to find the voltage passing through this capacitor.